Dear friends, today we will discuss conductor in electrostatics. Conductor. What is the behavior of conductor in electrostatics chapter? As you know, substances are classified into three types according to their conductivity. You know a little about this in class 10th. How current passes through a substance. One is conductor, one is semiconductor, one is insulator. But today we will discuss what is the role of conductor. You know, conductor, current passes easily through a conductor. Conductor has very good relationship with electricity, but insulator don't have. Okay, conductor is very sensitive in electricity. So today we will discuss about the role of conductor, the behavior of conductor in electrostatics. Let's start. First, point number 1. Electric field inside a closed conductor is 0. You can note this point. Electric field inside a closed conductor is 0. Why? The question comes to your mind. Why electric field is 0? Already you know this one. Electric lines of forces cannot passes through a conductor. They cannot penetrate the surface of a conductor because electric field inside it is 0. But why electric field inside it is 0? Okay, I'll tell. Suppose you take a closed conductor of any shape you take. Of any shape. Inside it electric field is 0. Okay, so electric also on the surface. On the surface and inside it is electric field is 0 in static situation. Static situation where no charges move, static situation, electric field on and inside a closed conductor is 0. Why it is 0 electric field? Okay, if I will tell you, suppose you will Gauss law and will choose any Gaussian surface inside it. Anywhere you want to find electric field here, then I choose one Gaussian surface like this. How many charges are enclosed by the Gaussian surface? No charge. Because no charge remain inside the closed conductor. No charges are here. So electric field inside it is 0. We can prove it by which law? Gauss law. So I can say you as no charges are there inside the closed conductor, so electric field inside it is 0. Okay. Now we'll go to the second point. The charges given to a closed conductor always resides on its outer surface. Again I repeat, charges given to a closed conductor always resides on its outer surface. Charges present always on its outer surface. Here the charges only present. Charges never present inside it, they present outside it. Why the charges present outside it? Outside the closed conductor. Okay, so what's the answer? So we can say electric field inside the closed conductor is 0. As electric field is 0, so no charges are there inside it. If any charge will present inside it, then it will have finite electric field. So no charges are there inside the closed conductor or inside the conductor. No charges are there. Charges always present on its outer surface. I told you first. Why electric field inside the conductor is 0? Because no charges present inside it. Why no charges present inside it? Second point. Why no charges present inside it? Because electric field inside it is 0. Is it correct? Is it the answer? We will discuss the answer like this? No. Why inside conductor electric field is 0? So that one we will discuss at the end of this chapter. At the end of this chapter I will tell you elaborately why electric field inside a closed conductor is 0. But why charges resides on the outer surface? Because there is no electric field inside. If you use Gauss law, then no charges can present inside the closed conductor. Okay, So now we'll go to the point number 3. On and inside a conductor, throughout its volume, in the whole volume, potential is constant. Potential is constant. Okay, so just like your equipotential surface. So the surface of the conductor potential is same everywhere. So the surface of the conductor behave as equipotential surface. But also the potential is same inside the conductor. Everywhere the potential is same. You may ask the question why? We must discuss. Okay, I can tell you, I can explain you this one. This also comes in exam. Electric field on and as well as inside the whole volume of the conductor, electric field is 0. If electric field is 0, then electrical expression, you know the relation between electric field and potential difference, E is equal to minus dV by dI is equal to 0. If derivative of potential is 0, then with respect to distance, then what about V? V is constant. We can prove it like this in exam, its question will come. So throughout the volume of the conductor means on and inside the conductor potential is constant. Okay, in this way you can prove it. And the surface of the conductor behave like one equipotential surface. I have told you also earlier this one in one video. The surface of the conductor, the best example of practical life example of equipotential surface is the surface of the conductor is an equipotential surface. So one thing I can tell you here, where you will apply this one, this concept, where you will apply? If I discuss one question, you see, this is a conductor, radius is R, suppose radius is equal to 10 meter, let's take, charge given to this is 10 coulomb, this is a sphere, conducting sphere, this is metal sphere, radius is 10 centimeter and charge given to it is 10 coulomb, charges resides on the surface, outer surface, okay. I'll ask one question here to find potential. Where will find potential? You find potential at this point, A, find potential at on the surface and find potential at C, outside the conductor. Okay, you can note this question also, it's a very good question. It gives you a lot important concept which you will use in other questions. So if I tell you to find potential at A is at a distance of 5 centimeter, 5 meters almost, taking SI unit everything in 5 meter. What is the expression of potential at point A? At point A, what is the potential? The potential at point A here, K, this K Q by R. You write the expression just like point charge. Just like point charge, because charges present on the surface of the conductor also behave as if they are present at the center. I have told you this one in the application of Gauss law. They behave as if they are present at the center. K Q by R. K 1 by 4 pi epsilon naught. You will put 9 into 10 power 9. What about this Q? Q is 10 coulomb. What about this R? R 5 centimeter. I will take R 5 centimeter. I'll then solve it. So this is the common mistake. You remember, when you are inside the conductor, as long as you are inside the conductor, if any part you are interested to find potential, don't take its distance, but distance will give in the question to confuse you. Okay, but don't take the that distance, rather you have to take here radius of the conductor. So this is radius of the conductor, that is 10 meter. 10 meter you will take there. Is it clear? You have to take that 10 meter. Don't write that distance which is given. You have to always take radius when you are inside the conductor. If I tell you, then you will solve it. You can solve it, no problem. So 10 cancel, you will be getting the value 9 into 10 power 9 volts. If I tell you to find potential at point B, K Q by R. So by default this will be correct. 9 into 10 power 9, Q is 10, R is 10, 10 cancel, so 9 into 10 power 9 volts. Now you sure? Potential at point A and potential at point B both has to be same. Because I told you potential is same throughout the volume of the conductor. So while putting the distance here, you will not take that distance what is given in the question. You will take its radius. Whenever I am repeating, you are inside the conductor. Then, what about the point C? Point C, just you behave as if all the charges are present at the center. You just behave as a point charge. KQ by R. KQ by R. You will put here 9 into 10 power 9. Q is 10. This distance is suppose given 20 meter. You take then 20. Okay. Then cancel. This is 4.5 into 10 power 9 volts at point C. So this is the basic concept I told you. You use this concept to solve many questions. But you remember this one. In one line I am telling you, as long as you are inside the conductor, while calculating potential, in place of a distance, you take a radius. You note this important line in red pen so that it will help you. This is a very important concept, very important line for you. Remember always this line. So this is about the potential. Then we will go to the fourth point. Fourth point now. What is the fourth point? The surface behaves like one equipotential surface. Okay, I told you the third point. Now we'll discuss the fourth point. Electric field lines meet the surface of conductor at 90 degree. Or electric field intensity is perpendicular to surface of conductor. You may tell, sir, you had already told this sentence in property of lines of force, but I had told this in property of lines of force, but I have not explained there. I have told you, I will explain in the next chapter. Now the time come. Now we will discuss why electric field lines are perpendicular to surface of conductor. Okay, this is the point. And also this one is not required to discuss. You already got the answer. The surface of conductor behaves as which surface? Equipotential surface. And I have told you in my previous video that two equipotential surfaces, how the electric field make how much angle with equipotential surface? 90 degree. Why 90 degree also we have discussed. I have told you two methods, two alternate ways to write. So that is the same answer you can write here on the surface of conductor. Why? Lines of forces meet at 90 degree. The same answer as we have discussed in equipotential surface. This was one property of equipotential surface. So you can write surface of conductor is an equipotential surface. So lines of forces meet the equipotential surface at 90 degree. Is it clear? So this is about point number 4. Now we will go to point number 5. Electric field just outside the surface of conductor. Why I am telling just outside the surface of conductor? Because I told you in the first point electric field on the surface of conductor is zero in static situation. Electric field just outside the surface of conductor. If I will take one conductor, any conductor you take, suppose like this, okay, I will find electric field. Suppose here I will find electric field just outside the surface of conductor, means its distance from this point, if it is r, then r plus dr, just outside. This is dr, very small distance outside, is sigma by epsilon naught. Electric field is sigma by epsilon naught n cap. N cap, if it is positively charged conductor, it will be perpendicular outward, normal to that plane, normal to that point, normal to the surface. Okay, so how we prove it? How we find electric field just outside the surface of conductor is sigma by epsilon naught n cap? We can prove it by using Gauss law. We have left, this is another application of Gauss law also. We have discussed, I think, 3 or 4 applications of Gauss law in the first chapter. This is also one application of Gauss law. Now the time came to discuss this application. Okay, this can come as a 2 marks question. Using Gauss law, find the electric field just outside the surface of the conductor. How will do this? Charges remain on the surface of conductor. Okay, here the charges present everywhere. Charges remain on the surface of a conductor. Clear? Then which density will come? Lambda, sigma, or rho? Okay, you are thinking the answer sigma because it is surface charge density. Charges present on the surface. Okay, so I am considering the point here. P point, I will find the electric field at which point? At point P, I will find the electric field. So to find electric field, what you have to do? Sigma, we consider sigma. Okay, so sigma is the surface charge density. It means sigma is Q by S. If we consider S surface area, charge is Q there, then Q by S. Then how will we find electric field? We have to use Gauss law. To use Gauss law, we need Gaussian surface. Then we will apply Gauss law. Gaussian surface you see. Now I choose one surface here. So here this is the conductor. So I choose one surface here in the conductor. So this is the surface. So in this surface, now use this surface area is S. I choose the charges present on the surface. Then this is your Gaussian surface. Is it clear? Now is it your Gaussian surface? Is it? No. Why? Why this cylinder is not your Gaussian surface now? Because the charges are not enclosed by the Gaussian surface. Same thing I had told you in while using the application of a Gauss law, application number 3, application number 2, while discussing. I have told you the charges are not present inside the Gaussian surface. They are present on the Gaussian surface. Because I start the Gaussian surface from the surface and charges are present on the surface. So you have to extend this Gaussian surface inside it also to enclose the charges present on the surface of the conductor. You have to extend it in the inside the conductor. You have to extend the cylinder. You have to extend the Gaussian surface. Now it is your Gaussian surface where you can use Gauss law. So using Gauss law, E dot ds q in by epsilon naught. Okay, then this is now closed surface. You know when cylinder comes, always I divide the cylinder into how many surfaces? Go to 3 surfaces, S1, S2, S3. Okay, so now put it here, E dot ds, E dot ds, then E dot ds. I will not write again close symbol because I split the cylinder into 3 surfaces. So where is the direction of electric field? Electric field is always perpendicular outward. Perpendicular outward direction electric field, positive charge, perpendicular outward. So let's take S1 surface. Which one? This surface is suppose S1. This is S1. Let's take this curved surface as S2. This is S2. This curved surface I am taking as S2. Let's take this curved surface as S2, then this side surface as S3. Okay, so now what happened here? For S1, what is the angle? E and S both are in same direction, so the angle is 0. E ds cos 0. For S2, what is the angle? E and S, what is the angle for S2? Okay, we will write for S2 angle is E ds cos 90. It's clear? Electric field is here, S2 is here. So angle is 90 degree. Then what is the angle for S3? For S3, what is the angle? You see, for S3 now. So electric field is there upward and S3 is where? Downward. So what is the angle between them? E ds cos, what angle now you are thinking? 180. So Q in by epsilon naught. So we did one common mistake. Students generally while writing they do this common mistake. Now you have to point out where we have done the common mistake. Here. How you tell the angle is 180? Inside the electric field, inside the conductor, is there an electric field? From the first point we have discussed, there is no electric field inside the conductor. Where there is no electric field, how you are telling the angle 180? How you are thinking the angle 180? Okay, you have not told, I write, but generally the students think like this, for which I wrote here. To just remove your common mistake, I have told you where you have common mistake, you just mark those points properly, so that you will not repeat this mistake in future. So here no angle, because here electric field is 0, not required writing angle, because there is no this electric field is outside. Inside it here at this point on this surface there is no electric field, because this side surface, plane surface, is present inside the conductor, where electric field itself is 0. From where angle will come? Okay, so this is 0. You are not writing angle there, because teachers always mark the common mistakes while checking the papers. So this is electric field is taken to outside constant, ds integration, this is 0 because cos 90, so q in by epsilon naught. Is it clear now? So next we go to our point C. So E, what is the ds integration? S, ds integration is S, so q in by epsilon naught. I have taken this surface, cylinder cross sectional area S, so q in by S epsilon naught, and what is this? Sigma. E is equal to sigma by epsilon naught. We will face this question as a 2 marks prove in your exams. Also you can write in vector form. E vector sigma by epsilon naught, which cap? N cap. Where n cap is perpendicular to the plane in outward direction, if it is positive charge, inward direction, if it is negative charge. So this is about the electric field just outside the surface of a conductor. Okay, so now we will consider one question you may ask here. Why I am telling just outside? Charges are present on the surface. Yes, as charges are present on the surface, if I take the Gaussian surface as the own surface of the conductor, then those charges will not be included in the Gaussian surface. They will be present on the Gaussian surface, and electric field on the surface will be 0, because you know charges present on the surface are not taken into account in Gauss law. They are not taken into account in Gauss law. So I told you, because I choose the Gaussian surface just outside. So always you will take out just outside the surface of conductor, electric field is sigma by epsilon naught. Now I will go to another point. From this you can generate one question. What question you can generate? You know that in first chapter, question number 29 of your NCERT book exercise, you will see we have left that question without discussing. We have left that question. Why we had left that question? To discuss here. That is actually question of this chapter, but is there in the first chapter NCERT book. So now let's discuss that one. What is that question? You can read the question from the NCERT book clearly, but just I am telling you, if a hole, small hole, if a tiny hole is cut somewhere, suppose I will cut a hole here. Let's cut a hole. One hole is cut here. Electric field at the hole is sigma by 2 epsilon naught n cap. Prove it. The question is like this. On from a charged conductor, if we cut a tiny hole, electric field at the hole is sigma by 2 epsilon naught n cap. Prove it. The question will come like this. How will prove it? So now let's come. It's also one important question, very rare question. Okay. So how I prove that electric field is here this much, sigma by 2 epsilon naught. We know the electric field on the surface is sigma by epsilon naught, just outside the surface. But here it is given if hole is cut, it is sigma by 2 epsilon naught. Now you think, suppose that part is not cut from the conductor. You just think now, you divide this conductor into two parts. One is the rest part, one is the cutting part. How much is cut from the surface? Now let's write, let E1 vector is electric field due to the cutting part. It is the electric field due to which part? Due to the cutting part. And E2 vector is the electric field due to the rest part. E2 vector is the electric field due to rest part, E1 vector is the electric field due to cutting part. So what is your question now? To calculate E1 or E2? Your question is now to calculate E2, because after cutting the rest part electric field is asked here. After cutting that portion, the rest part electric field is asked here. So your question is to find E2, not E1. Your question is to find what? E2. Okay. The whole conductor consists of both cutting part and the rest part. The whole conductor consists of cutting part and rest part. You now imagine when the part is not cut, what is the electric field inside? Electric field inside it is 0. When the part is not cut, okay, when the part is not cut, you just imagine the part is not cut from this, then electric field inside it is 0. Inside electric field is equal to 0. Inside the conductor electric field is equal to 0. Then inside the conductor here electric field who provide? We have divided the conductor into two parts. Who provide here? The cutting part provide as well as the rest part provide. Cutting part plus rest part provide the electric field here, and that is 0. Because I told you the cutting part is there. Okay, it is not cut. Then E1 vector or E2 vector, we need E2 minus of E1 vector. You understand? What is the meaning of this? Why electric field inside is 0? Because electric field due to cutting part and rest part both are equal and opposite, means they are equal in magnitude. E1 vector and E2 vector are equal in magnitude but direction opposite, for which electric field is 0 inside it. Now you conclude here. Now you come just outside the point when the tiny hole is cut. When the tiny hole is cut, what happens here? Now you see. When the hole is not cut. Now again, when the hole is not cut outside, this is inside. Now you come to outside. Outside, what is the electric field? Sigma by epsilon naught n cap. What is the electric field when the hole is not cut? Outside, I am telling. Outside, this is the expression just before I proved it. Okay, for the whole conductor. But this is combination of E1 vector and E2 vector, sigma by epsilon naught n cap. Sigma by epsilon naught n cap. Okay. Now, what about this? Implies that E1 vector and E2 vector both are equal in magnitude. If they are equal in magnitude, now you see outside electric field is non-zero. Both are equal in magnitude, but electric field is non-zero means the two vectors are added. But inside it with 0 means two vectors are subtracted, they are in opposite direction. But here two vectors are added means two vectors will be in same direction. Okay, for which electric field is first finite value, so we will write it 2E2 because both are equal in magnitude and they are added most because electric field otherwise will not come as a finite value. 2E2, so E2 vector is equal to sigma by 2 epsilon naught n cap. Your question was E2, now you got it. Now you got it. So again I am telling you electric field inside it is 0. This indicates due to cutting part and due to rest part, electric field are equal in magnitude, opposite in direction inside. But outside it is non-zero because they are in same direction. But magnitude is equal, we have also shown it there. Okay, so I wrote here 2E2, then E2 vector is equal to this much. Now we will go to the last property of the conductor. Okay, so before discussing the last property, I am telling you, it's now physics teaching is too much. Now I will tell you a small story before discussing the last property. So you are thinking now sir has been teaching physics, now start telling story. Okay, so story is like this. Once one rich man wearing a costly silver chain now is going to travel in a train, and in stations you know many thieves are available. So one thief start following the rich man. and the rich man went and sat on his place. Then the thief also went and sat close to the person, rich man. And the rich man now travel. Rich man has to go to long distance, whole night journey, and the thief is thinking, how I will take the chain. You know, the person is rich means has a lot of money, and gold means also he knows how to save his money. Then what happened? Even after evening, then the night came. Then the thief thought, okay, when in night the person, the rich man will sleep, at that time I will snatch I will take the chain. But the rich man is not sleeping. It become 11 p.m. Then they take their dinner, but still the rich man is not sleeping. The thief is also thinking, how I will take the chain. Then the thief start doing acting. Then the thief, what the thief did? Now thief slept. Just thief do acting of sleeping. Then what happened? After some time, the thief slept and starts snoring. Then the rich man now saw the thief. Thief is in deep, completely now slept. Then what happened? Then the rich man went to sleep. Then when it become 2 p.m. night, 2 a.m. night, then the thief suddenly woke up and thought, I am here to take the gold chain, but why I am sleeping? Then the thief suddenly started searching the gold chain. And he searched the bag of the person, the bag of the rich man, and also everywhere he see, also the pocket, the rich man hung the shirt, his shirt here, also searched the pocket, everything everywhere. The person searched, the thief searched, but could not able to get the gold chain. In frustration, being tired, then the thief again slept. And in morning, the thief slept late in night. Then what happened? The thief also woke up in late morning, 7 a.m., 8 a.m. Thief woke up. But when the thief woke up and saw, then the rich man is sitting, completing his morning work after a bath, lighting everything. Now is sitting, wearing the gold chain also. Then he thought, I could not able to get the gold chain, and the gold also was not in his neck. But now from where the gold chain come? But now unfortunately the destination of the rich person came, and the rich person now left the platform. And now thief again started following. After some distance now, thief went and touched the feet of the rich man and asked, you man, please tell me where you kept the gold chain so that I couldn't able to find it. I am a great thief. Still I couldn't able to find it. If you tell me the place, then from where you kept it, if I know, then I will use this trick in my next. Again when I will go to steal one chain, then I will apply it. Then the rich man told where he kept the gold chain in night, where he kept. The rich man told her there, when you slept, I kept the gold chain in your pocket. You searched everything, my bag, my pocket, my shirt, everything you searched, but you couldn't able to get, because I know you will never search your own pocket. So I kept the gold chain in your pocket, and in morning when you wake up in late, then I wake up earlier and then take out from your pocket and again wear it. Then the thief will salute the rich man. But why I told you this story? What is the moral of this story? I had listened somewhere this story. Actually the moral is like this. We never see inside us what happened, what we are thinking. We never bothered about that. What we are doing, we are never bothered about that. But we are bothered what our in surrounding what happens. Or what the people seem to, we always blame others. He's doing that, he's doing this, you are doing the wrong thing. But what wrong we are doing, we never see. The moral of the story is like this. And the person who told me this story at that time also told this one, that you close your eye and you do self-analysis. Okay, what mistake you are doing? But you are thinking, in physics, why sir is telling this type of story? I told you why. Because thief has a good relation with the gold chain. Thief has a good relation with gold chain. Same thing, conductor has a good relation with charge. Gold chain can be safely inside, can be safely stored in the pocket of the thief, who is very sensitive to gold chain. It can be safely stored inside the pocket of the thief. Inside the thief it can be safely stored. Same thing I am also going to tell you. Conductor is very sensitive to electric field, electric charge. But the substances which are affected by external electric field, affected by external electric charge, then we can store it inside the conductor. Because inside the conductor electric field is zero. It can be safely stored inside the conductor. Anything affected by external electric field can be safely stored inside the conductor. No harm, no external electric force can disturb it. Okay? This is called, this one phenomenon in physics called electrostatic shielding. Shielding means we seal the electric field. Electric field cannot enter inside a closed conductor. We seal it. So the things which will be affected can be stored safely inside it, like the gold chain in the pocket of the thief. You may tell me, sir, please tell me one practical example so that we can able to understand clearly. Who is very sensitive to external electric field? You are very sensitive. You, the human being, the animals, from when they are getting affected by external electric field during lightning. When lightning happens, a large amount of current comes to earth. And if that current will pass through your body, then what happens? You know then what will happen? We will convert one to Tandri. This happens. Then what will do? If at that time you will sit inside a closed car. Closed car. Car is a conductor. Closed conductor. Nowadays, but cars are made up of fiber, but not all costly cars, they are made up, they are very closed conductor, strong conductor. Car can be treated as a closed conductor. If you sit inside a car, then external electric field, the lightning will come, it will not affect it. You may tell, sir, in car there are glass, it is not completely closed, but still it is closed. The charges will be present on the car, on the surface of the car, the car will be charged. But no harm, nothing will happen to you if you are inside it. If you touch the inner surface of the car, also no problem, because charges present outside the surface of the car. So, during lightning, it is safe to be inside a car because electric field inside the car is zero. Also, during lightning, it is safe to be in a closed room in your house. When you are in childhood, when the lightning happens, what mother tells generally, okay, you now enter in the room and close the doors, remain inside the room. Why? Because this room also can be behave like a closed conductor. We are using metals while using this house. When you make a house, then we are using some metals also, some rods, everything we are making. This just behaves like a metal case. So be inside a closed house, be inside your house during lightning, because you will be safe, electric field is zero inside. Then, but don't stand in an open field during lightning. Don't stand. Don't stand also under coconut tree, because coconut trees are generally tall And when the lightning now comes from one potential, higher potential to here 0, and earth is 0 potential. This is just a current pass from higher potential to here to 0. When current comes during lightning and coconut tree is just earth, projection of earth but in upward direction, it try to touch the coconut tree. Okay, try to touch the coconut tree. Now if suppose the coconut tree is here, this is not the proper diagram of a coconut tree. Okay, when the lightning current comes, when the current is coming like this, rather going to here earth, it will now pull here. Shortcut path. Here is getting the 0 potential. This is 0, also this is 0 potential. So don't stand near the coconut tree. Also, you should not plant any coconut tree close to your house, which is a bad practice. Our ancestors generally treat like this. Because lightning happens, when lightning happens, it will touch the coconut tree. Okay, so I told you about electrostatic shielding. Inside a closed conductor, electric field is 0. This is called shielding. So one question may come in your exam. Why it is safe to be inside a car during lightning? Because electric field inside the car is 0 due to electrostatic shielding. What is safe to be inside the house? Because also electric field is 0. So due to electrostatic shielding, so in lightning no harm will happen. But one question we can discuss from this: can gravitational field be shielded like this? Is it possible? Can we shield gravitational field? No, we cannot shield gravitational field. Why? Because gravitational force is independent of medium. We cannot shield gravitational field, but we can shield electrostatic field. Inside the closed conductor, field is 0. So this is the conductor in electrostatics. Thank you.